Okay, let's go ahead and get started with section 2.4. In section 2.4, we're going to be considering confidence intervals, which are closely related to a concept that you may have heard before, and that is margin of error. So we're going to be computing margin of error quantities for examples that closely resemble those that we've considered thus far in chapter 2. Okay, let's go ahead and get started. Recall a statistical hypothesis test is a process by which data is used to measure the amount of evidence for a carefully stated research question. The process of conducting a test requires us to identify the parameter of interest and furthermore provide a value for that parameter to be tested. In contrast, a confidence interval is used to provide a likely range of values for a parameter. Confidence interval does not require pre-specification of that parameter. The goal of a confidence interval is to estimate the amount of inherent variation in a measurement over the repeated sampling. A couple of definitions. So what is a confidence interval? A confidence interval is a likely range of values for a parameter. How about margin of error? The definition of a margin of error is the acceptable amount of inherent variation in a measurement over repeated sampling. Oftentimes, margin of error is considered when conducting polls, and that's what we'll look at with our first example. So let us consider example 2.4.1. This particular poll was done by the Star Tribune, which is a newspaper from the Twin Cities. A total of 625 registered voters from Minnesota were surveyed. The survey question under consideration here is related to opinions regarding stricter gun laws in the United States. So what was the survey question that the individuals were asked? It was, do you support or oppose stricter gun laws in the United States? If we look at the data that was presented, there were 350 out of the 625 people that supported stricter gun laws. This 56%, which is the quantity that we're going to use in computing the margin of error, was obtained by taking 350 and dividing by 625. If we consider those that oppose stricter gun laws, there were 194 of those individuals, and 194 divided by 625 is where this 31% is obtained from. Finally, there were 81 people that were undecided when asked this question. That represents about 13% of the total people surveyed. I took this information and went ahead and presented it in a graphic as shown here on the top of page 43. I went ahead and combined the opposed category and the undecided category, as my goal here is to compute a margin of error quantity for those that support. So I'm going to compute a margin of error quantity for this 56% here. Okay, let us consider the following set of graphs here that will help explain the relationship between confidence intervals and margin of error. In this first example, or the example presented at the top here, there is a lot of inherent variation being shown here. Now, what do I mean by the inherent variation? What I mean is that if this poll surveyed another 625 people, these numbers are going to change a little bit. So if we consider those that support, maybe next time it's not going to be 56%, but it might be 54%, or it might be 52%, or it might be 57%. There's certainly going to be some variation in this 56% over repeated sampling. And that's the idea here of what is being shown in these graphs. In this first, I have shown quite a bit of inherent variation. In other words, that 56% could drift all the way down to 40%. And then I'm saying, well, that 56% could drift all the way up to about 72% here. Now that entire range from the 40 up to the 72% is what we call the confidence interval. So what is the confidence interval's associated margin of error? Well, the margin of error quantity is just simply how far up, that would be the positive margin of error, and how far down, that would be the negative margin of error, that we go to reach the edge of the confidence interval. So in this particular case, the center was at 56%, and what I have drawn here goes all the way down to 40%. 56 minus 40 is 16%. 56 plus 16% is what I used to reach up to 72% here. So for this first graphic, the confidence interval goes from 40% up to 72%, and its associated margin of error would be plus and minus 16%. So what would it look like if there was only a moderate amount of inherent variation? Well, then we wouldn't drift down as much, nor would we drift up as much. So in this middle graphic, the confidence interval looks like it goes from about 48% up to about 64%. That would be about plus or minus 8 percentage points. So for this graphic here, the margin of error would be plus or minus 8%. On the bottom graphic, I don't have much inherent variation at all. So over repeated sampling, this 56% is not going to change very much. It looks like what I have drawn here, it goes down to about 52% and up to about 60%. The associated margin of error for this case would be plus and minus 4 percentage points. So which situation are we in with this example? Do we have a lot of inherent variation, or do we have not much inherent variation? And that's what we'll consider next. We will use a simulation model to try to estimate how much inherent variation exists in this statistic, the 56% over repeated sampling. So let's go ahead and look at a simulation-based approach. This is approach number 1. What we're going to need in order to build a simulation model is the number of trials and also an appropriate percentage to build the model. The number of trials here is just going to be represented by the number of people who took the poll, which is the 625. The percentage that we're interested in here is the percentage that responded in the survey, which was at 56%. So the proportion that supported stricter gun laws from the survey, that was at 56%. The scope of inference for this problem is all Minnesota registered voters. Okay, so if we go back up and look at the description of the poll that was, or the survey that was done, it says the Star Tribune Minnesota poll interviewed 625 Minnesota registered voters between April 15th and April 18th about gun ownership. So the study participants here are the 625 Minnesota registered voters. But they're using this information in this poll to try to talk about Minnesota voters in general. So the scope of inference here is Minnesota registered voters. The parameter then is just the proportion of those who support stricter gun laws in the United States. That's the quantity that I'm trying to estimate. That's the quantity that I'm trying to understand. Now from my study, as I said, there were 625 Minnesota registered voters who participated in this survey. So I'm going to use that in my number of trials when I'm building my simulation model. Now the statistic, or the measurement of interest that I care about here, which is sometimes called a point estimate, is just the proportion of survey respondents who supported stricter gun laws in the U.S. And that's simply the 350 divided by the 625, or the 56%. And we use the quantity pi hat to represent that number. Okay, so now we're ready to build our simulation model. We're going to go ahead and build the simulation model using the reference distribution app that we used earlier in this chapter. Here I'm going to use 10,000 repeated simulations in order to construct my reference distribution. So how do I find the lower and upper endpoints of a confidence interval? Recall that a confidence interval is a range of likely values for a parameter over repeated sampling. The 5% rule is used to separate likely from unlikely values in a distribution. For simplicity here, only two-sided confidence intervals are going to be considered. Those are by far the most common. Finally, confidence intervals and margin of error are usually computed using the proportion instead of the actual counts. So we usually compute a margin of error quantity for a percentage. So in our reference distribution app, we're going to want to make sure and select proportion of successes when we're building the graphs. So let's go ahead and consider just a first guess here at the endpoints of our confidence interval. So in the as extreme and as box, I'm going to go ahead and just make an initial guess at where I believe the number that separates the unlikely from the likely outcomes. So I'm going to be on the edge of the distribution again, and it looks like I put 51% here. So when I put 51% here, it looks like that the proportion of samples that are as extreme or more extreme than 51% in this reference distribution is about 1%. So using the 51% and its associated endpoint on the upper end, which again is just the mirror image of that 51%. So if I go from 56% down to 51, that's a drop of 5 percentage points. I need to go up 5 percentage points. Again, these are two-sided confidence intervals. So when using 51% up to 61% as my endpoints of my confidence interval, I'm a little too conservative. I only have 1% of the distribution here that's being identified as unlikely. So let's go ahead and modify that guess just slightly. So here I'm using 52% in the as extreme as box here. And when I do that, using 52% and its associated upper limit of 60%, I get about 4.8% of the observations as being identified as unlikely. And again, using the 5% rule, that's pretty close to what I need here. So 52% and 60% seems to be about right for the endpoints of the confidence interval. Let's go ahead and just keep guessing here. What if I use 53%? So if I use 53% and its associated upper limit of 59%, it looks like the percentage of dots that are identified as unlikely here is about 13%. And that's too liberal. That's quite a bit above the 5% limit that we're shooting for. So it looks like 52 to 60 is about right. Now we can actually refine this a little bit more if we wanted. So let us consider guess number 4 here. In guess number 4, I went ahead and just inched up that lower endpoint just a little bit more. So instead of 52% here, I went ahead and put 52.1% in the box. And would I put in 0.521, and its associated upper limit then would be 0.599, I get really close to that 5%. I get 4.9%, I guess, if I round that. So that's even closer to my 5% target. So using 51.9% and 59.9% as endpoints for my confidence interval would probably be my best bet here. So the 95% confidence interval then, using the simulation-based approach, is going to go from 52.1% up to 59.9%. The associated margin of error here, which again is just the distance from the middle to the edges. So for the positive margin of error, how would I actually compute that? Well, the upper endpoint is at 59.9%. The middle of the reference distribution is at 56%. So if I take 59.9% and subtract 56%, that's where I get that 3.9% margin of error. Likewise, for the negative margin of error, I would just need to start at 56% and determine how far it is to the lower endpoint. And that lower endpoint is at 52.1%. So that's where I get my margin of error quantities of plus 3.9% and negative 3.9%. So for this particular problem, the confidence interval goes from 52.1% up to 59.9%, and its associated margin of error is at 3.9%. Now this is a 95% confidence interval because I'm identifying the middle 95% of my observations here. So again, most often we compute 95% confidence intervals because we're using the 5% rule when determining unlikely from likely outcomes. Okay, let's go ahead and do the normal theory approach. So there's certain limitations to using a simulation-based model. We considered those in the previous section when we were talking about p-values. One of those limitations is that if I do a different simulation, I'm going to end up with a slightly different reference distribution, which means I'm going to get a slightly different confidence interval. The way that we alleviate that problem here when computing confidence intervals is through the use of a normal curve or a bell curve. Now, the normal curve is actually being used to approximate the binomial probability distribution, and that approximation works pretty well. So as you would notice here, for our simulated reference distribution, a bell curve seems to match that pattern pretty well. And in fact, when we use a bell curve, so when we use a bell curve approximation or a normal curve approximation to this binomial probability distribution, we actually only need to concern ourselves with two quantities. And those two quantities are, where is the bell curve centered at? So at that expected value, which here is going to be at that 56%. And we also need to concern ourselves with the sample size. The sample size helps us determine how much inherent variation we have in this distribution over repeated sampling. So the sample size here is 625. Now recall that the binomial probability distribution is based on an infinite number of repeated samples. So this bell curve, if we use the bell curve, we're going to get the same exact answer when two different people use these calculations. So what are those calculations? Well, it starts with a statistic or a measurement of interest, sometimes called a point estimate, and that is identified with the pi hat quantity. In this particular example, the pi hat quantity here is at that 56%. We have the upper margin of error and the lower margin of error. In order to compute the upper margin of error, what we do is we take this 1.96 quantity, call that the interval multiplier, and then we multiply it by this formula here, which is the square root of pi hat times 1 minus pi hat, all divided by n. This quantity here, the square root of pi hat times 1 minus pi hat divided by n, is commonly referred to as the standard error. So this is how we obtain the positive margin of error. The negative margin of error is just going to be the opposite of that. So it's the same quantity just going in the other direction. So instead of having a positive sign here, we have a negative sign. Now in order to reach my upper endpoint, all I need to do is start in the middle, which is at that 56%, and then add my margin of error to it. That's how I obtain the upper endpoint. And for the lower endpoint, I would start at that 56%, and I would just subtract the margin of error quantity here. So that's how I obtain the endpoints for my 95% confidence interval. Let's talk a little bit about that interval multiplier. The value of 1.96 is used because we are interested in capturing the middle 95%. So using 1.96 ensures that the 5% rule is being used to separate the likely from unlikely values. If we were to increase that interval multiplier, suppose we were to change that 1.96 to maybe, let's say 2.5 or something. Well, if we were to increase that interval multiplier, that would push these arrows longer. In other words, the margin of error would increase. It would go up further here, and then when we're doing the other side, it would go down further here. So if we were using negative 2.5 here instead of 1.96, that would just push that arrow out a little bit further. If we were to use 2.5, we wouldn't be going after the middle 95%. but we might be going after the middle 98% or 99%. Okay, so if I push these margin of errors out, I'm going to identify more values as being likely here. So let's go ahead and answer these questions here. What happens to the margin of error and confidence interval when the interval multiplier is increased to, say, 2.5? Well, the margin of error will increase, which will push the upper and lower endpoints out further. The confidence interval would contain the middle, say 99% or so, instead of the middle 95%. Likewise, if we were to reduce the interval multiplier, so if we were to change this to a quantity such as 1.65 or so, that would bring this margin of error in a little bit. Okay, it would make the confidence interval a little bit narrower. And instead of the middle 95, we might be going after the middle 90%. So a lot of textbooks and PowerPoint slides will talk about changing this interval multiplier. To be honest with you, everybody uses the 5% rule. So we're just going to leave those quantities at positive 1.96 and negative 1.96. How about the second question here? Explain why the statistic or the point estimate is always within the confidence interval. Well, it's always within the confidence interval because that's the starting point. Okay? So when I build the confidence interval, I start here at that statistic, and I build my margin of error up from that, and I build my margin of error down from that. So the statistic is always contained in the confidence interval. In fact, it is the middle of the confidence interval. And we'll talk a little bit about that again when we go to interpret this confidence interval, what we mean by that likely range of values. So we'll hit that again here in a moment. So the confidence interval is not for a statistic, but it's for a parameter. Okay, we are trying to figure out a likely range of values for the parameter, not the statistic, because the statistic is always going to be right in the middle of that range. Okay, how about the calculations then? Well, the calculations are fairly straightforward. Once you have the formula, we know that the margin of error is going to be positive 1.96 times that standard error, and then the corresponding negative 1.96 times that standard error. So if we just plug and chug the numbers in here, again, the pi hat quantity is at 56%. I need to multiply that by 1 minus 0.56. And then I divide that entire quantity by 625, take the square root of it, and multiply it against 1.96. And when I do that, I get plus or minus about 0.0389, which I've rounded to plus or minus 9%. Or excuse me, 3.9%. So how do I get the upper end point of my confidence interval? Again, as I've stated, I just take the 56% and I add that 3.9%. For the lower, I'm going to take the 56% and subtract 3.9%. So my confidence interval, based on the normal theory approach, is going to go from about 52.1% up to 59.9%. So that's the calculations there for the confidence interval and the margin of error for this particular problem. One thing to notice is that this confidence interval matches what I got with the simulation-based approach. And it should, because I used many dots there. I think I used 10,000 repeated outcomes when building that reference distribution. So I have a pretty good idea of what that reference distribution looks like. So I would anticipate that the quantities that I compute from the reference distribution would be the same as those based on the theory. Okay, what is the interpretation then of this confidence interval? Well, the interpretation here is it is the proportion of all Minnesota voters. Go ahead and highlight that first. It is the proportion of all Minnesota registered voters that would support stricter gun laws here. Okay, so again, that confidence interval is trying to identify, okay, the outcomes for those in our scope of inference, which are all Minnesota registered voters. And I was looking at those that support stricter gun laws. So let's go ahead and read that interpretation from front to end here. It is the proportion of all Minnesota registered voters that would support stricter gun laws in the United States is likely to be between 52.1% up to 59.9%. Let's go ahead and consider some comments here. So as I just said, the confidence interval identifies a range of likely values for the parameter, which relates directly to the scope of inference, not just the study outcome. So the outcome from the 625 study participants was the 56%, as is shown here. Now, the purpose of a confidence interval is to again give you a range of likely values for that parameter. And the parameter here again represents the proportion of people that support stricter gun laws. And the people that I'm talking about there are all Minnesota registered voters. Talk a little bit about the normal approximation. I said that a moment ago that works well for most situations. So when does the normal distribution fail us then? Well, it fails when our reference distribution gets too close to zero. So here I've shown you an example one, a reference distribution that actually gets truncated off here at zero. Okay, we're talking about a proportion of people, and that proportion cannot go below zero. So I get this distribution that's kind of truncated on the left-hand side. Well, the normal approximation would not work very well for a situation like this. The general rule of thumb that is used to identify those situations is provided here on the top of page 50. Most software packages make it pretty easy to add the margin of error to a graph. So here is how that normally looks. It's got just a little bar here that shows you kind of how much I would expect that 56% to go up or down. This particular margin of error was put on this graph in Google Sheets, and that is shown here on the bottom of this page. You simply need to select the bar that you want to add the margin of error to. You can double click, select Customize, and then underneath the Series tab or the Series menu, you can specify a margin of error quantity here. I've entered that as a percent here of 3.9%, and once that is done, it'll add the margin of error to your graphic for you. All right, let us consider a second example. I'm going to stick with the same theme with that survey question, but here I'm going to look at younger people versus older people and their support for this particular question. So I have 18 to 49-year-olds. How many 18 to 49-year-olds were in this survey? There were 299 of those individuals. 176 of those 299 supported stricter gun laws. That's about 59% if we do the calculation. 176 divided by 299. That gives me about 59%. If I'm doing 50 and older in that age group, there were 172 people that supported stricter gun laws. In this particular group, there were 324 people in total. So 172 divided by 324 is where we obtain this 53%. So let's go ahead and compute the margin of error for both the 18 to 49-year-olds for those that support. So let's go ahead and compute a margin of error for this bar here, and then also the 50 and older group. Let's compute a margin of error for that quantity. Calculations again are simply 1.96 times pi hat, 1 minus pi hat divided by n. And I went ahead and did those calculations in a spreadsheet. You can just type those in real carefully here. You can do these on your calculator as well. In fact, there's actually apps out there that you could probably use that will compute this quantity automatically for you. The calculations aren't that bad. So here I'm just typing equal in a cell, just type equal 1.96 times the square root. I'm using the 59%, using that as a decimal there. Got to enter that in as a decimal, 0.59 times 1 minus 0.59 divided by the number of people in that group, which was 299. So again, let's go back up and look at our table. Okay, there were 59% of the people in this particular age group that supported stricter gun laws. And there were 299 individuals. Likewise, for the 50 and older group, I would just take 1.96 times the square root of 0.53 times 1 minus 0.53, all divided by 324 there. And when we do that, I get a margin of error for the younger people at 5.6%, and I get a margin of error for the older people at 5.4%. So those two margin of errors are actually pretty close to one another, and that is because the total number of people surveyed here is pretty close, and also the pi hat quantities are pretty close. The 50 and older age group, their margin of error is just slightly less because they have a little bit more people in there. Notice that n, the number of people, is in the denominator of this quantity. So as the number of people increases, the margin of error is going to decrease. If we take those endpoints or those margin of errors and compute the confidence intervals, so how would I do that again? Well, for the 18 to 49-year-olds, I would take the 59% and I would subtract 5.6%. That's where that 53.4% is coming from. So again, 59% minus its associated margin of error up here is 5.6%. And when I do that, I get 53.4%. If I take 59% and add the 5.6%, I'll get the upper endpoint for the confidence interval, and that's at 64.6%. I do the same thing for the 50 and older age group, except here I'm going to be starting with 53%, right? Okay, so their percentage, the starting point, is at 53%. So take 53%, subtract 5.4, take 53% and add 5.4, and that's where I get these quantities here. Okay, the interpretations are going to be very similar to what we had above. We are talking about all Minnesota registered voters again here. Okay, so we're talking about all Minnesota registered voters. But here, if I'm talking about age group 18 to 49, it would be all Minnesota registered voters whose age group is between 18 and 49. Okay, so that's part of my scope of inference for this particular group here. And again, we're talking about those that would support stricter gun laws. So let's go ahead and interpret that entire quantity. The interpretation of the 95% confidence interval is the proportion of all Minnesota registered voters whose age is between 18 and 49 that would support stricter gun laws in the United States is likely to be between 53.4% up to 64.6%. Okay, and these are 95% confidence intervals, right? And as we've said, those are by far the most common. 95% confidence interval implies that we are using the 5% rule for determining likely from unlikely outcomes. Okay, some additional comments here. Let us consider the formula for the margin of error. Again, it's that plus or minus 1.96 times the square root of pi hat times 1 minus pi hat divided by n. In order to cut my margin of error in half, I'm going to have 4 times as many people. So that's a little bit counterintuitive. Some people believe that in order to cut my margin of error in half, I just need to take twice as many people. But that would be incorrect. And the reason that is because that sample size quantity sits underneath the radical sign, sits underneath the square root. Okay, so here I'm just showing you some of the calculations. I'm going to use the 18 to 49 age group. This first line is what we had up above. There was 299 people there. Let's suppose this poll, though, instead had 1,196. Now, I got that number because that is 4 times larger than 299. So I'm going to use 1,196 here in the denominator instead of 299. And when I do that, you can see that the margin of error goes from about 5.6%, okay, with 299 people, and it actually drops to about 2.8% when I use 1,196. Okay? So in order to cut your margin of error in half, what you actually have to do is take 4 times as many people. How about the following? With a little algebra, the formula for the margin of error can be expressed as follows. Okay, so let's go back up here and look at that. I can take this 1.96 stuff over to the other side, just divide the right-hand side by 1.96. And then I guess I would have to square both sides in order to get rid of the square root. And with a little bit more algebra, you can determine that n is equal to pi hat times 1 minus pi hat, all divided by the margin of error divided by 1.96, that quantity squared. Now, why is this important, or how might we use this? Well, suppose that somebody has decided that they want a poll, they want their outcomes to have a 3% margin of error. Okay, so they want to have a 3% margin of error when they get done. And it's believed that the statistic, or the point estimate, is going to be about 28%. So again, I'm just making up numbers here to show you how this actually works. So I want a 3% margin of error, and I believe that my point estimate, or my statistic, is going to be about 28%. So I can go ahead and put 0.03 in here for the margin of error. I got the 1.96. I'm going to put pi hat. I'm going to put 0.28 in there for my pi hat quantity. And I can just push through these calculations. And the sample size necessary in order to achieve a 3% margin of error is about 860 people. So that will tell me how many people I actually need to get in my survey in order to ensure a 3% margin of error. So that's commonly done in polls, in that we use, somebody has predetermined what they want their margin of error to be, and then they go out and select that many people. Okay, that does it then for section 2.4. That does it for section 2.4. I hope you better understand how to compute margin of error quantities for a single proportion. All right, thank you very much.